Thanks for the introduction again. As announced, this talk is a joint talk by myself, Franz Rammerstorfer, and Nicholas. So I will present this use case Carlos talked about beforehand. So our autonomous robot Spider and its components and its architecture. And the main part of this talk is Nicholas' part, where he will deal with the application of his new or pretty new safety analysis method, which is called HD3, hazard-driven decomposition design and development, applied to one of the functions we will port on the SELENE board, namely the collision avoidance function. Let us start with some motivational aspects. So as Carlos already said, the objectives of in SELENE or within the project is, of course, the validation of this platform in the automotive domain. So we want to assess the performance, the security, and the safety capabilities of the SELENE platform and its components. But from our perspective, so as virtual vehicle, we aim at getting a safety certifiable hardware software stack for our robot Spider. So we decided to integrate the SELENE platform in our robot and execute two vehicle functions in a safe and secure, hopefully safe and secure way on this platform. So we will go to our goal, to safety certifiable stack, just piece by piece, and we start with two functions. So to first things first, of course, I need to introduce the Spider. The Spider is the Spider means smart physical development and evaluation robot. And the goal of the Spider is to perform automated reproducible test drives on proving grounds. So in a nutshell, the Spider is a mobile hardware-in-the-loop platform for the development and testing of autonomous driving functions. So due to its open design, it's possible to extend the Spider with some sensors, some edge computing devices, or whatever you want to test entire perception systems, decision-making algorithms, or control systems. And the main benefit of a system like the Spider is that the test drive itself is ensured, the safety of the test drive is ensured by the Spider itself due to its emergency remote control or its collision avoidance functions, and the test team who is using the Spider can focus on the task at hand. Okay, so I talked about two vehicle functions we want to port on the SELENE platform, and here are some details about it. On the one hand side, we want to port the path tracking function, which enables the Spider to follow a predefined global path. So it's more or less a waypoint follower. And this function is decomposed into two sub-functions in a path tracking function controller, which is safety critical, and in a path tracking function manager, which is kind of security relevant due to its openness to the world, to the operator. The second function we want to port, or we have already ported, is the collision avoidance function. By the way, here the abbreviation is COA, and later in the slides it's CAF, but this is just a little thing. It's the same thing. Don't mix it up. It's the collision avoidance function. So the collision avoidance function enables the Spider to stop or to slow down its operation when there are some obstacles around. So it initiates an emergency brake in case of danger. That's, of course, a safety critical function. Both ports are based on ROS2, as we already heard by Carlos. Now ROS2, the robot operating system version 2, is available for RISC-V. That's also a very nice outcome of the SELENE project, which was done by Siemens Germany. And if you want to use it, just have a look at this URL. where you can find the ports and the build system for RISC-V. So actually, we've chosen ROS2 since we want to stay with Linux, but the ROS1, the first version of ROS was kind of prototype-like. So this next iteration of the ROS framework is more for real-world applications, not like just for research or prototyping. Okay. To understand what we have done or what we want to show within this use case in the SELENE project, I want to I've sketched this components diagram of the Spider before integrating the SELENE platform. So the Spider consists of a bunch of sensors like LiDARs, GPS, odometry sensors and stuff, and consists of two control units. On the one hand side, the high-level control unit, which runs all vehicle functions on a normal COTS computer on Ubuntu Linux. And before this project, all vehicle functions are based on the ROS1 middleware. The second computing device right now is Infineon AUX MCU, which is communicating with the actuators of the Spider, like the motion controls, the steering stuff, and the battery. Integrating the SELENE platform. Now the components diagram looks like here. We integrate this platform in parallel to the high-level control unit, and we will shift two functions, as already said, path tracking and the collision avoidance, on this platform to have at least a part of the functionality of the Spider in a safe and secure way. So all what we need to do there is connect the SELENE platform, here is a little picture of the evaluation board we use in the project. This is a Xilinx VCU 118, a pretty big FPGA board. We will connect just this board onto our gateway and communicate this via Ethernet and run all the software for the two functions on that board. All the remaining functions will be hosted by the high-level control unit. Okay. Now a closer look on the SELENE board, where we will want to show the capabilities of SELENE, of course. So we will divide the cores. We have a 6-core system there into the following functions. So like for the jailhouse hypervisor, as Carlos said, we will use the jailhouse hypervisor to partition the system. We need a root cell. Then we need a secured cell for the path tracking manager function, since this has open ports to the operator. And then we will have a 2 out of 2 architecture for the safe cells, one for the path tracking controller and one for the collision avoidance. So this 2 out of 2 architecture will be monitored by another product outcome of the SELENE project, the root voter, which was done by OpenTech, by Nicholas Koberger. This hardware device, which also is synthesized in the FPGA, will vote these two cells, but for the safety details, we will hear much more in the talk of Nicholas. So in the end, within this use case, we will be able to demonstrate a lot of the hardware and software safety support, which was done in the SELENE project, and we will run this mixed criticality application like sketched on the right-hand side. Okay, as the last slide from my side, I want to give some details on the collision avoidance, since this is the basis for the talk of Nicholas. So the collision avoidance function, which we want to port, is just this little red square on the right-hand side. So only this decision-making algorithm, am I within a danger zone or a safety zone, is ported to the SELENE board and will be analyzed by Nicolas' method. All the other things like the LiDAR pipeline and the Cloud Fusion and pre-processing stuff will still run on the high-level control unit. So just this red little square on the right-hand side will be analyzed. Just to be clear. Okay. So that's all from my side, and I will hand over to you, Nicolas. Can you hear me? Hopefully you're here.
So you hear me now?
Yeah, fine.
Okay.
So
thanks, Franz.
We are on problem statement.
Yep. Well, as Charles said right at the beginning, the SELENE platform is addressing a lot of the key safety problems by providing self-monitoring, which is a very traditional approach to safety. But as he also noted, we need to use different methods now than in traditional systems, like monitoring statistical properties of processors. And I would say that's one of the ways of how we're trying to capitalize on complexity rather than fight complexity. And I think this is one theme that is very important to keep in mind, that these traditional low-level methods are reaching their limits. At the same time, when we look at monitoring, we also have to know what we need to monitor and which impact on the safety properties of the system a failure of such a monitoring or one of the intended mitigation methods would have. So this is how this part of the talk actually connects to the big picture of SELENE, and in between we have the spider as the use case, and as Franz just explained, the actual functionality of the collision avoidance function is seemingly not very complex, but the overall complexity is in the system itself. We have multi-core, we're using novel technologies, machine learning, management of complex data types that are not state-of-the-art in traditional safety systems, and this brings the overall complexity level to significantly higher levels than traditional systems we're used to using. And the consequence of that is that we no longer have the ability to build up a neat software stack, hardware, software, generic software that is fully certified, and then pop our safety-related application on top, adhering to a well-specified interface, and we're done. We have to actually figure out how we can look at the overall system. So we have a number of challenges that grew out of this increased complexity. Just to mention one is seemingly conflicting needs between security and safety. Traditional safety wants deterministic systems. Security wants non-deterministic systems in the sense that they are no longer predictable, so that an attacker cannot sort of know where to jump to do a return on libc attack or a buffer overflow or whatever. So these, at a high level, are conflicting needs, and as Charles explained, we can actually rejoin these abilities by finding ways how we can use the non-determinism for safety in a sense of an inherent diversity. Another key point is, that's my personal view, I think that we see a very strong trend toward using pre-existing elements. That's not only Linux, but we have many safety-related projects that are using GCC, which is an open source project that was not developed with safety in mind. We see libraries, communication libraries being used that were not developed with safety in mind. So finding ways how we can integrate pre-existing elements or actually build entire systems with pre-existing elements become important. Franz mentioned ROS. I'm not aware of any serious intent to certify ROS as a safety-related element. I would consider that an almost unmanageable task from the overall complexity. But of course, using components within the safety-related system will induce some safety requirements on these elements as well. So the question that we actually have when we're talking about functional safety is, how can we get enough understanding of the system so that we know how it's going to behave under the expected conditions? The traditional answer was know all failure modes of the base layer of the hardware of the operating system, if you had one, of your library stack, and from this knowledge of the deterministic behavior of these elements, then conclude the safety functions of the upper layers. For systems that are using pre-existing software, that doesn't really work very well, and using complex hardware, that starts failing because we get too many emerging properties and interdependencies. So we're taking a different approach. We're saying we have to boil down the context that we actually have to look at to the minimum context for the specific use case. That's where this hazard-driven decomposition comes from. We don't look at a functional design, and then when we have functionally done, ask how to make it safe. We drive the entire design process by a hierarchical hazard analysis, and that's what I will be introducing. Next slide, please. So new methods are sort of frowned on in the safety community for good reasons, because we have tendencies, and when new problems pop up, that we try to come up with new tools, new methods, because it looks like a quick fix, and sometimes it's better to adapt existing methods to gain from the previous knowledge, and especially to also benefit from the compliance to safety standards. We decided, after working with complex systems and actually certifying some Linux-based systems in the rail industry, that the available methods cannot do the job, and we need a new method. So the target is a new IEC 62158 Edition 2 compliant method. We are looking at the draft Edition 3 to ensure compliance there, but for mid-complexity, we don't see any major changes. Now, we look at how system analysis starts. Every system starts initially as a Type B system. That's specified in 61508 Part 2, 74412, and basically says, 74413, a Type B system is a system where you either do not know all the failure modes, or you don't understand the behavior of the system under a failure mode, or you don't have adequate data to support your safety claims. If we look at a new system, even if you're using traditional systems, all three of these properties are not satisfied initially, and the safety process is intending to transform this Type B system into a Type A system. So at the end of the process, you should know all failure modes. You should understand the system under system behavior under failure condition, and you should, of course, have adequate data. Note that these three conditions are, of course, interconnected. If you don't know your failure modes, and you obviously cannot understand or have adequate data. That's a small inconsistency in 61508, because it does allow you to continue working with a Type B system. Okay, so the question is then, since 61508 and its derived standards focus on traditional Type A systems, low complexity systems, where traditional methods are suitable, we need to look at how can we handle this transformation with a highly complex system that is using novel technologies. Just mentioned before, multi-core. I'm at least not aware of any certified multi-core on this planet, machine learning, and high complex elements, even if the element that we will be looking at the moment is not that complex. Okay, so what HA3 is trying to do is to boil down this type B system in small steps until we achieve a level of understanding of the system that is compliant with the requirements of type A system. All failure modes will not be known, but all credible or relevant failure modes will be known, and the behavior under failure condition should be reasonably understood. Of course, HA3 does not address the third condition of adequate data to bolster your claims. That's out of scope here. Next slide, please. How to approaching complex systems.
Yep.
So the approach that we developed in SIL2 Linux project was that we say we actually have three initial columns. We have the target system, you have your use case, you know what you're trying to build. In a traditional system, we would go into maybe a design reference mission or directly into FMEAs if it's or one of its variants. If it's one of the systems that we already have a good understanding, if you're building the 5th generation of System X, then you probably can go more or less straight into a failure mode and effect analysis because you roughly know the failure modes, or you can do hazard and operability studies directly on the specification of the systems. And from there, you would derive your safety requirements. Now, if we're doing this for a new system, that's the part of DRM has up FMEA style approach that we're trying to replace by a exploratory method. HAZOP is an exploratory method, but it has its limitations. And this has to fit into context of the standard. If we look at part 1 of 61508, it's quite classic, almost a waterfall model going from context to scope to hazard and risk analysis, and then specifying the safety functional requirements. And the interesting thing about that is that part 1 is system level. It's prior to actually allocating any of these functions to hardware, software, or other technologies, as 61508 will term it. So you're actually, in part 1, you're looking at it at a technology agnostic level. You're saying, I have a safety function, I don't want to have collision. In the case of the spider, what do I have to do? And you don't care how you're going to do it. You could have somebody, a driver, physically riding on the spider, providing this collision avoidance function in theory, at least at the level of 62158. So you're going into this in a technology agnostic way, and then going into the allocation. Now, as noted, we assume that pre-existing elements are going to be important. That's why we introduce this 7x extension in the context of SIL2 Linux, how to do the selection. And I'm not going to go into the details of that, but the key issue here is that you have element candidates. We all can think of different pre-existing operating systems that could be suitable for such a project. There's multiple incarnations of libc, of tools, of communication stacks, and so on. Or as Franz mentioned before, 2 different versions of ROS, and then you can look at these element candidates and say which potentials do they have. Even if they were not developed for safety, we can look at safety potential. Which diversity do they have? Do they have timing guarantees? Do they follow coding standards? Are they well specified? And so on. You basically are getting a good point, bad point list to enable you to do proper allocation in context of your use case. So while you're doing that, we have to develop the interdependencies of these elements, because that's one of the characteristics of complex safety-related systems, that these interdependencies become important, some cases even dominant. I mean, it's more or less a definition of complexity that you have emerging properties. And from these dependency tree, we then can develop architectural requirements. What can be joined? Can we co-locate, for instance, a collision avoidance function and the path management on one node, and a collision avoidance function and some other safety-related or non-safe function on the second node, or what potential are there? And this is an iterative process where you're trying to develop these potentials, and that final step of this first round is to have preliminary architecture, basically a set of architecture constraints. I'm going to focus on this first part because that's where we currently are in the process, and that's where we also have those examples. So next one, please. Following 62158.
Yes.
So we're developing this use case. Now, in this case, the use case is actually given, so we're not strictly developing it from scratch. We have an existing prototype or specification, but still we are sort of adjusting it or tailoring it to fit the needs that emerge from applying the analysis in the context of the standard, and getting certain constraints that we have for the candidate elements that we want to have. We heard that on the SELENE platform, we have hypervisor available. We have low-level assurance mechanisms built into the hardware. So that means we can then, when we look at these elements, for instance, we have this statistical tracking of the execution instruction, then we can use the inherent diversity of complex piece of software like the Linux kernel because we have the assurance. And this interplay of the elements is what's important to develop in an early phase, what could be used from different elements, and that's where we really start diverting from this traditional safety approach. So, as I said, it's a layered process. So we start out with a technology agnostic analysis, where we're really focusing on design and high-level requirements issues. As we know from analysis like the HSE study, with a nice title, Out of Control, that shows that a significant part of the accidents are actually due to requirements and design failures, not so much implementation failures. And one of the problems is that as engineers, we tend, I do, and I know a number of other engineers that do, we tend to sort of allocate the problems to the technological, to the implementation level. We say the operating system failed. We very rarely see an error and say, oh, it's a design fault or it's a requirements fault. So doing a technology agnostic analysis helps us sort of distill out what is really a design problem, what are the design implications, and what the layer below is actually doing. When we have the technology agnostic analysis, where we're asking for instance, measuring of distance, but we're not specifying which technology we're using, and we just ask what can go wrong with measuring distance in a very generic way. And we go into the unspecific technology-aware analysis, where we have this first allocation, hardware, software, other technology, as 62158 calls it, in clause 7.6 in part 1. And then we branch out into part 2 for system and part 3 for software. And at that level, we're saying we know it's an operating system, or we know it's a library, or we know it's a piece of hardware. It's VHDL that will run in an FPGA, but we don't care about which operating system it is, which libc version it is. And finally, we go into the lowest level of technology aware. We're looking at really the specific technology version, Linux kernel 4.9, 19, glibc 2.21 or whatever. The point is, one of the key challenges that we have with complex systems is not the initial certification, but managing of changes that will occur. Franz mentioned security as one of the important topics. We are in a connected world. No matter how concise you build your multi-core safety-related system, if it's connected to the outer world, you're expecting 2 to 4 CVEs per year that will affect you, and that means you have to do impact analysis. If you just have one hierarchy, that means you would have to start at the top level every time. If we have a decomposed hierarchical system, and I have a severe bug reported for kernel 4.919, then I can mitigate it as a technology-aware specific layer, but my analysis for the unspecific and for the technology agnostic is not reopened necessarily. So next one, how we build up these layers, maybe relate a little bit more clearly what this is about. Analysis layering, please.
Yeah, we're there.
So we start out with a design intent statement. You will see one in a moment. And we go into the high-level analysis. And from this analysis, we get a whole bunch of findings where possible deviations could occur, and searching for indications and mitigations of these deviations. And these are then, in part, allocated to derived elements. That's what the derived technology agnostic analysis is about, or they can be set as requirements for the individual items. We'll see the process in a moment. And that sort of gives you the next necessary context for the candidate and technology selection, because that's one of the big problems that we saw in the past 20 years of working on safety, is that very often we're confronted with a ready-to-go system, a technology is integrated in there, and we should then make it safe. And then you basically are saying, well, you're using floating point, although it's not necessary. You have to certify your floating point unit, and that can end up being a showstopper. If you turn the process around and say, let's extract the minimum set of functionality and that we actually need to implement the design intent, then we also, with a focus on certification and safety properties from the very beginning, then we just can lower the risk of actually ending up in this situation that we have a prototype and we can't certify it. I mean, automotive industry is the best example at the moment, with I don't know how many billions invested in autonomous driving. We have hundreds of cars or fleets actually driving around with safety drivers in them, and nobody has a clue how they're going to certify these brilliant systems. So I'm not saying that we could do it with this method, but it's definitely a problem that has to be solved. Okay, the other layers are not so important for today, but basically we are iteratively going down until we have a final system architecture and a final element specification. That's really the goal, and you're going down always with analysis of the items that you have in the specific context, and then possibly deriving new items. It doesn't mean that we always have to derive new items, but it can happen. What's the point of doing this in this way? Next one, please, complexity management. The observation was that if we try to analyze a complex system from the very beginning as one system, or sort of as one integrated system from the design down to the technology, what happens is that we have very high complexity in the indication mitigations or the actual implementations. for instance, Spider, we get a point cloud and we have to find the nearest point in this point cloud. Not a hugely complex operation, but it sort of distracts from the simplicity of actually simply saying, I need the distance. The technical details can be quite involved from how to manage this data. So the idea is to say, we want to have a clear understanding of the context, of the conceptual mitigations that are being implemented in this context, that they are correct, independent of how they are actually being implemented. To put this in context of Spider, the question that you're trying to answer is measuring the distance to the nearest object sufficient to be safe? That's sort of the type of question you're trying to answer, rather than asking, is the signal of the LIDAR and the error in the LIDAR signal, is that going to be a problem? You just ignore that problem and just say, we're measuring distance. Tell me first if this conceptual mitigation of collision by measuring distance is sufficient. What sampling rates do you get? What dynamic properties must you guarantee? You're making assumptions that objects will intrude into the safe zone of Spider from the side and from the front. You're not assuming that they're falling from the top. At least I would not imagine that this was one of the assumptions that was made. And then you go into the technology aware unspecific layer, then you're looking mainly at architectural, software system architectural issues. You're again ignoring implementation details. You're looking at allocation issues. Do you need replication? What independence can you capitalize on? As I said, capitalizing on complexity is one of the themes that I think is very important in modern safety-related systems. That's our focus in this second technology-aware but unspecific layer, where we know what's being done by software, hardware, operating systems, and so on. And finally, we go into the technology-aware, and that is a layer where basically the abstraction is now at a very low level. We know exactly what we need. We don't care that it's a distance to an object. We're just looking at point cloud data at this point. We don't need to consider a lot of system context for the implementation at this level, because we know from our architectural analysis before which interdependencies or independence exists, but the actual implementation of mitigations and indications can have a very high complexity. And that's really the goal, or the grand goal of complexity management here. It's not only that we're boiling down the context, but we are striving to split up the actual complexity here in this way. So next one, please. Look at the design
Niklas,
intent.
I have to push you a little bit, 5 minutes. Is this okay for you?
Oops, okay. Yeah, I'll try. So
Thank
next one, the design intent, really quick. Well, not too surprising. It's trying to avoid collision, and in case that a violation of safe zone or hazard zone is detected, if something is too near, it will activate a flag and to initiate an emergency braking. Okay, next one, please. The initial functions, functional requirements, safety requirements that we started out with from virtual vehicle, getting the threshold, that's sort of the initialization problem, the first one, then finding the obstacles in the safe zone, in the danger zone, and then deciding what to do, either stop the vehicle, have an acoustic or optical indication, and initialize a maneuver for braking. Okay, next one, please. Roll within Spider. Yeah. It's protection against close encounter and actual collision. For us, the analysis also added that we are sanity checking a lot of the inputs. So that's something where we can harvest safety assurance that CAF would be providing for other elements in the system that actually have nothing to do with CAF. But if the collision avoidance is monitoring certain properties like the sanity of the odometer and so on. One of the first things that we noticed is that we started out with this input list, initially occupancy grid and config file, and during analysis we then added some input that we need because we need speed, we need the direction, we need system level time. I think that the engineers initially designing the functionality were clear of that, but it just turned out that they didn't list it. So that sort of popped up. On the output side, we just added one output. That wasn't so dramatic. Okay, let's look at the actual process side. Sort of to summarize a little bit what we just were talking about. Next slide, please, applying HA3. We started out this design intent left top corner, then we go into the hazard and operability analysis, very traditional, using the guide words you see here below, more or less part of as well as well-known hazard guide words. We do that per item, emit all the SACs, put them on the SAC list, then go into the consolidation, and if we have consolidation element, then we do the whole thing again. And from that, we're deriving sort of the hierarchical design of the overall system. Okay, next one, just briefly, it's a random grab, the high-level analysis element 23 in this case. One of the elements was end feedback, feedback to the environment, and that's sort of what you would get. You see the interpretation, additional information was considered because the guide word is as well as. Possible causes, boundary of status not found, status format not well defined, and so on. And then which mitigations, or in this case, indications, and on the right side, then mitigations would you have? And that's encoded then in the high-level SACs, the high-level safety application conditions. And we'll briefly look at one of those safety application conditions on the next slide, please. That's typical what a safety application condition would look like. That an adequate communication handshake shall be selected. The direction in this case up, I will explain that in a moment. And then you have simply a specification what is needed from this safety application to be satisfied. So not really rocket science, you're just saying you need to have certain properties of this handshake process. Okay, highlight analysis, next one, please.
Yep.
Give you a little bit of a picture what that looks like. This somewhat simplistic graph is basically this x-axis is just the number of the safety application conditions, on the y-axis the occurrence rate, and you see that on number of SACs, about 22, 23, only occurred a single time during the analysis. All others occurred multiple times. Those are single that are candidates for local implementation. Everything that's multiple times you would probably want to push into libraries or consolidate into elements. And it gives you a first view of the criticality of SACs. Obviously, the SAC that's all the way on the right side that is called on 20 times in the overall system, that one would be a critical or highly critical one, and the ones that are single use might be less critical. Now, of course, that's a little bit dangerous statement because not every deviation has equal weighting with respect to violating a safety target. But it's a first rough approximation. So this is what we ended up when we analyzed collision avoidance. We had 19 SACs at the process level. We call those up SACs. Process level SAC is something like system testing, configuration management, or something like that. And we had a number of generic implementation level SACs, which we call down SACs, or down safety application conditions, and 37 were specific. So it looks a little bit wilder than it is. We say we have 85 safety application conditions, but actually the specific ones are not that many. And we had a number of assumptions that we have to make for the external elements that we call then external SACs. Okay, interesting side effect of this process was that during the review and reuse of SACs in different contexts, we actually had a number of internal findings, actually 12 findings where we had incomplete specification or erroneous specification in our previous analysis of items. The number of derived items was 2, so we had a total of 8 items then. The consolidation of the SACs that we could push into the derived items was only 17, actually quite low count from our experience up to now. And the new SACs during analysis of derived items was then 26. So you do see that this iterative process can reach a relatively high complexity, but again, goal is type A system, all failure modes known, behavior and default condition understood in adequate data, with the last one adequate data not really in context of HT3. So last slide, conclusions. So this is only the first analysis, fourth analysis cycle of an safety-related project that we have been doing. So we still have some development ongoing in the method itself, some adjustments of processes or process steps, but it's getting less and less. It is quite experimental. We are in contact with TÜV Rheinland for the qualification of this method, and we do hope to actually not get a formal qualification, but a review statement from TÜV when we're done with the whole process. The most important thing for us was that the design actually looks quite different than what you would get from a functional design. Functional design would probably be 1 or 2 functions. For the CAF, we ended up with 8 functions so that we can assure safety properties and actually utilize some architectural protection mechanisms that might not be traditionally used. Yeah. Next step for us is to apply it to more complex problems, get an independent verification and validation. Sorry for the and sign missing between the V and V. I think that's a tech glitch. I forgot to escape the ampersand there. But independent verification of the method is, of course, important, and then start growing the complexity of the element that we're analyzing. This is an open source project, so both the tools and the method is released under an open source license, specifically CC BY SA 4.0. So it's a Creative Commons based release, and tools are under GPL. So if anybody is interested in looking into this in more detail, we're happy to share.